Hi everyone. So in this video, I just want to introduce a concept of a subgraph, a subtree, and a spanning tree. And the idea here is a very common mathematical idea that you see in many different contexts, many different situations. And it's the idea of sort of a subset or sub-collection of something that exists. So maybe you recall a long time ago, we were looking at sort of voting theory and weighted voting systems, and we had a bunch of players, P1, P2, maybe up to Pn, and we talked about winning coalitions. And there was this notation which is set notation, where we considered all of the players. And then inside of this, we considered some subset of players that would win a vote of some sort. So I don't know that we'd have some set like this, for example. So a subset is just a collection of players or elements of a given set that may or may not be all of them uh, combined. And so you can kind of look at this. There's this symbol here, which mathematicians use, which is to indicate containment. It says that the set on the right is contained in the set on the left. Um, in other words, the set on the right is a subset. And why am I mentioning this? Well, we're not talking, and nor are we going to talk about um, weighted voting systems for the at this time, but we're talking about graphs. So we have some graph here, and what we want is we want to consider sort of subgraphs of this graph. And what would be a nice way uh, to indicate that? Well, we can make our edge list of our graph. And the edge list is a set of edges. So let's write it out for this graph. We have AB, we have AC, we have AD, we have BE, we have CE, we have CD, uh, we have DH and DG. Um, we have E, G, and E, or EF and EG. I'm actually going to move this all the way down below here. Um, and we have, let's say, F, G, F, H, and then G, H, and I believe that's all we have. So we can encode the entire graph so long as there's no isolated points uh, as just an edge list. And then if we want to define a subgraph, we can just take any subset of this edge list, and that will give us a subgraph. So this is the idea of a subgraph, is we just take a few of these guys. Let's say we take CD, DH, we'll take E, we'll take all three of these. And I don't want to leave out any. Maybe we'll take A, B, and AD, put these guys in. Um, well, let's just leave this. This is fine. And we can go ahead and consider this. And you might say, well, what does that look like? Uh-oh, looks like I didn't duplicate, but I moved. Let me duplicate this. What does that look like? Well, we can go ahead and just see what it looks like. So let's just get rid of all the edges here. Um, we want to see what it looks like, let's go ahead and see. So I have an edge between AC. I have an edge between AD. I have an edge between CE. I have an edge between D and H. I have an edge between E and F. EG, and FG. This is my graph. Now, you can include singletons, so it's not completely true if you have singletons that this is just a subgraph is just the subset of edge lists because you may want to include an additional vertex. But typically, if you're talking about a subgraph, it's going to be a graph whose vertices form a subset of the vertex set and whose edges form a subset um, of the edge set for the original graph. So let's assume for the moment that I don't actually care about B as being in the subgraph, and that's perfectly fine. So then this gives a subgraph. So this is a subgraph of the original. So you can always talk about subgraphs. It's just a collection of the edges, not all of them necessarily, but um, but yeah, that's the idea of a subgraph. So then, what is a subtree? Well, a subtree, let's define it. So a subtree of a network or graph, we'll stick with network, um, is a subgraph that is a tree. That's it. So it should be connected and it should satisfy one of any of the many properties that trees satisfy. So um, the n-1 edge condition, the all bridge condition, so on. So if we take a look at an example here, we'll go ahead and duplicate this. Oops, I over duplicated. Um, and I lost D here. If we want a subgraph of this, that is a subtree, there are many. So, you could go ahead and just shade maybe, oops, several red and get this as a subtree. So the edges in red already form a subtree because the red part is a subgraph and it's a tree. Great. So there's a special kind of subtree, which is called a spanning tree. And these are of great importance in applications of graph theory. So let's say what a spanning tree is. So a spanning tree of a network is a subtree which touches, let's say, every node. Sometimes we say it spans the graph. So alternatively, we say the subtree spans the graph. Okay, so we can actually extend the subtree that we have drawn here to make a spanning tree. In fact, we can do it in many ways. Um, so all we have to do is we have to keep on going. We sort of do what we did before in a prior video when we were talking about a game of making trees, but we restrict ourselves to just adding edges um, that are in the graph that we're dealing with. So or links. So I would, if I want to continue adding links, because I haven't hit all of the nodes yet, there are many ways I can do it. But what I'm not allowed to do if I want to make a spanning tree is to make a circuit. If I so in other words, I cannot choose C and D as a part of my spanning tree because that would make a circuit. At least if I want the already existing red graph to be part of it. So I could choose, for example, B and E, and then I could choose A and D. And I haven't connected F and H, and there are many ways to do it. I mean, I could do this, I could do this. There's a lot of different ways, so I want to be clear that what I'm doing here is not unique, but rather we can just go ahead and choose one way of doing it like this, and then say here. So now I contend that I have a spanning tree, and well, let's see. So if you um, if we take this whole thing, let's duplicate it, and let's just take a look. We'll just erase the blue edges because they're too distracting, and see what we get. And I think if when you look at it without the blue edges, you can see, yeah, there's only one path between any two vertices. There's no circuits. But if you really want to do a numerical count, you can go ahead and see we have 1, 2, 3, 4, 5, 6, 7, 8. So we have n equaling 8 nodes, and we have 1, 2, 3, 4, 5, 6, 7. We have m equaling 7 edges. And there's this n minus 1 edge condition, which is satisfied here. It's certainly connected, and so we're in good shape. All right, so this is the notion of a spanning tree. And that's one we're going to focus a lot on. And why would you care? So let's just say what's one reason that you might want a spanning tree? Well, if we go back and we just, let's say we go back and um, we'll just color everything here back to blue. And we have this kind of situation where we imagine that this is a these are a bunch of houses or maybe cities or something, and what you have in front of you is a potential network of roads that are being built between these cities or houses. And what you want is you don't want to build that many roads, but what you do want is you want to make sure that if you're in one city, you can always use roads to get to any other city. So the way you can save the most money is by finding a spanning tree. And the point is if I just build roads along the spanning tree, then I know that there's a way, given if I reside in any one of these cities, to travel to the other. It may be longer than building all the roads, but I can always do it. So it sort of makes sure that everything is still connected. And you can use this example with with like power grids or plumbing systems or however you want to put it, whatever your favorite network application is. Um, so so right. Um, okay.